Welcome to the deep dive. Today, we're looking into something pretty critical for anyone working with LLMs and code, how these models handle really, really long context. Because when you start applying code-specialized LLMs to, actual large-scale projects, the amount of context they need, all of the related files, definitions, classes, it just blows up. We're talking tens of thousands of tokens. And the second that happens, you run into some serious problems. First, API costs can shoot way up. Second, the core transformer tech with its quadratic attention complexity means processing time gets drastically longer. And maybe most importantly, even if a model can technically ingest all that context, studies show it often gets, well, lost in the middle, struggling to find the relevant bits.
Absolutely. And that lost in the middle problem is even worse with code. Code isn't just text, it's structured, full of dependencies that aren't always obvious from the words themselves. If you try standard text compression methods, they often just mangle the code, breaking the syntax. So we really need something specifically designed for code structure, its dependencies. Existing solutions, they just don't quite cut it.
Which brings us to our focus today, LongCodeZip. It's presented as a new framework, sort of plug and play, built precisely to solve these long context issues for code models. The idea is to get high compression without hurting performance on coding tasks.
Yeah, and maybe the best way to understand LongCodeZip is to first see why the other methods fall short with code. We mentioned general text compression, like LLMLingua, great for natural language, maybe removing common words. But for code, it doesn't understand syntax or structure, it just cuts based on text patterns, often leaving you with unusable code snippets. Then there's retrieval augmented generation, RG. RAGU tries to help by finding and retrieving only the parts of the context that seem similar, lexically similar, to the task or query.
And that works okay if the connection is obvious, right? Like if you're completing function A and it directly calls function B with a similar name.
Right. But code dependencies are often much more subtle. The source material gives a great example. Imagine you need the LLM to complete a Python function called train model. To do that correctly, the model absolutely needs the definition of a separate class, let's say config, which might define things like learning rate, number of epochs, model parameters. Really critical stuff.
But there's probably not much textual overlap between the words train model and config.
Exactly. So RG, looking purely at word similarity, might see that vital config class definition as low relevance, maybe ranking it way down the list or skipping it altogether.
And without that config definition, the LLM just can't generate the right code. It's functionally blind to that non-lexical but essential dependency.
That's the core failing LongCodeZip aims to fix. It shifts the focus from similarity to usefulness, using a metric called approximated mutual information, or AMI.
AMI, okay, how does that work?
Instead of asking how similar is this context snippet, AMI asks, how much does this snippet reduce the model's perplexity for the given task? Perplexity, for listeners, is basically a measure of how surprised or uncertain the model is about what comes next. High perplexity means high uncertainty.
So if adding a piece of context makes the model much less uncertain about how to complete the train model function, that piece of context gets a high AMI score.
That's it. AMI is calculated as the initial perplexity of the task instruction minus the perplexity given the context snippet, PPLQ, PPLQCC. A big drop in perplexity means a high AMI score.
Which means that context is really helping the model predict the output. It captures relevance based on function, not just words. So that crucial config class, even without lexical overlap, would likely get a high AMI score because it's essential for predicting the train model code.
Precisely. It picks up both the obvious links and those deeper structural dependencies that RAG misses.
Okay, that makes sense as a core metric. So how does LongCodeZip actually use this AMI scoring? The paper mentions a two-stage approach.
Yes, it's a hierarchical strategy. First, there's a coarse-grained compression stage. Think of this as the first big filter.
How does that work?
It starts by breaking down the entire source code base into larger chunks, specifically at the function level. These are usually semantically self-contained units.
Got it, function by function.
Then each of these function chunks is ranked using that AMI score relative to the task instruction. We calculate how much each function helps reduce the model's uncertainty about the task.
So you identify the most helpful functions first.
Right. And then, under a set token budget for this course stage, it selects the top-ranked functions. Functions that don't make the cut, the ones deemed less relevant by the AMI score, are effectively filtered out. They might be replaced by a simple placeholder, like a comment, just to show something was removed, keeping the overall structure visible, but drastically cutting tokens.
Okay, so that first pass gets rid of a lot of the noise, focusing on the most relevant functions. But those functions themselves might still be quite long. What's the next step?
That's the fine-grained compression stage. This focuses on pruning within the selected functions. And it starts with something quite clever, block-level chunking.
Block level, not just lines.
No, it's smarter than that. It segments the function's code into smaller semantic blocks. The interesting part is how it finds these block boundaries. It uses perplexity again. As a model reads through the lines of code in a function, a sudden sharp increase in perplexity on a specific line usually indicates a shift in logic, the start of a new conceptual block.
Ah, so it's using the model's own understanding of the code flow to find natural breaking points, not just arbitrary line counts.
Exactly, it divides the function into meaningful units.
Okay, so now you have these smaller semantic blocks within each important function. How do you decide which blocks to keep and which to prune?
Two key steps here. First is adaptive budget allocation. Remember how functions got ranked by AMI in the coarse stage? Well, functions that scored higher initially, the ones deemed most critical, get a larger token budget for this fine-grained stage.
That makes sense. Keep more detail in the most important parts.
Right, and less critical functions get pruned more aggressively. There's also a safeguard. Very short functions, say less than 5 lines, are kept entirely to avoid breaking things.
Okay, so budgets are set per function. Then what?
Then comes the dynamic block selection. For each function, and within its allocated budget, it uses the classic AO1 knapsack optimization problem.
Knapsack. Can you break that down a bit?
Sure. Think of it like packing a backpack. Your backpack has a size limit. That's the token budget for the function. You have a bunch of items you could pack. Those are the semantic blocks within the function. Each block has a value, its AMI score, how useful it is, and a weight, how many tokens it takes up.
Okay.
The knapsack problem is simply figuring out which combination of blocks gives you the highest total value, total AMI, without exceeding the weight limit, token budget. It's a way to maximize the information density you keep.
That's a really neat application of that concept. So you end up keeping the most valuable code blocks within each function, respecting the budget constraints. Let's talk results. Did this actually work in practice?
It seems so. The framework was tested across several tasks: code completion, code summarization, and question answering about code bases, using different models like DeepSeek and Qwen 2.5.
And the key finding.
The main takeaway, what they call RQ1, was that LongCodeZip consistently did better than the baseline compression methods, LLMLingua, RA, and others mentioned like Diet Code, Slim Code. It achieved up to a 5.6x compression ratio, reportedly without sacrificing task performance, sometimes even improving it.
5.6x compression is significant. What did the ablation study show? Like, which parts of LongCodeZip mattered most?
That was quite revealing, RQ2. The coarse-grained ranking using AMI, that initial step of picking the most relevant functions based on perplexity reduction, was found to be the most impactful component by far. It significantly outperformed just using similarity for ranking, yielding about a 7.9% higher score on edit similarity for code completion.
So identifying the functionally relevant chunks up front is key.
It seems to be the foundation. The fine-grained steps, like the adaptive budget and the knapsack optimization, provide further gains by making the selected context even more information-dense. But the big win comes from that initial AMI-based filtering.
Now, you mentioned performance sometimes improved. Tell me about the results on closed-source models like GPT-4. That sounds counterintuitive.
It does, but it's one of the most interesting findings, RQ1, RQ4. On the RepoQA task, which involves answering questions about a repository, LongCodeZip didn't just match the performance of using the full uncompressed context, it actually beat it when used with GPT-4o and Claude 3.7 Sonnet.
Beat it.
How? For GPT-4o, the average score went from 87.8 with no compression to 88.9 with LongCodeZip. The thinking here is that the compression acts almost like a distraction filter.
Ah, so even massive models can get confused or sidetracked by too much irrelevant information in the context.
That seems to be the implication. By removing the noise and focusing the model on the truly essential code snippets, LongCodeZip might actually enable clearer reasoning, leading to better answers.
That's fascinating. It reframes compression not just as a cost-saving measure, but potentially as a performance enhancer by improving focus. What about the practical side speed and cost?
Huge benefits there too, RQ4. Using Qwen 2.5 Coder 7b as an example, LongCodeZip cut input token cost by 77%. And perhaps more critical for developers, it reduced the time it took to get a response, generation latency, from about 15.7 seconds down to 6.6 seconds.
Wow, less than half the time. Was the compression itself slow?
The overhead for compression was only about 2.6 seconds in that test. So the total time compression plus generation was still significantly faster than just generation with the full context.
And is this practical to implement? Does the compression step itself need a giant model?
That's another good point they addressed, our Q3. The approach seems to generalize well. They found you could even use a much smaller model, like a 0.5 billion parameter encoder, just for the compression step and still get good results.
So you don't need massive GPU resources just to run the compressor. That makes it much more accessible.
Exactly. It lowers the barrier for adopting this kind of advanced context management. So wrapping it up, LongCodeZip's advantage seems to come from its code-aware, hierarchical approach. Moving beyond simple text similarity and using that AMI or perplexity reduction metric allows it to really zero in on functional dependencies, preserving the core logic needed for coding tasks, even after significant compression.
And perhaps the final thought for you, our listener, comes from that ablation study finding. The AMI ranking itself delivered the biggest performance boost. It suggests that helping these incredibly powerful models perform better on complex code might be less about just feeding them more and more data and more about intelligently filtering it. If even top models like GPT-4o perform better with compressed, focused context, maybe the real challenge isn't the size of the context window anymore, but rather managing the model's attention within it. Perhaps less is more when it comes to relevant signal.